So welcome to lecture 32 of MCS 471, an introduction to numerical analysis, where today we continue our exploration in initial value problems. So in a way, this will be our fifth and last lecture on initial value problems. So today we close off a chapter. We've covered several methods already. So today we are going to continue our exploration of numerical methods. So in particular, we will start with predictor-corrector methods. We will make the distinction between an explicit and an implicit method. In a way, we have already seen this way of working with the modified Euler method. We will generalize this idea, and that will lead to the class of Adams-Bashforth, Adams-Moulton methods. Pairs of methods we have seen with the embedded pairs of Runge-Kutta methods. What is the relationship between Adams-Bashforth, Adams-Moulton, and the Runge-Kutta methods? Stability is important, so every method has an order, which gives us the expected accuracy, but sometimes it doesn't go always the way as we expect. So we will see a general way to derive the stability of a method, distinguish also between one-step and multi-step methods. We will end with variable step methods, where we use different h values, combining the formulas, the values that we have for those different steps. All right, that's the plan for this lecture. So let us first define some terminology. So first and foremost, we have a standard formulation for an initial value problem defined by a right-hand side function and an initial condition. We apply numerical differentiation to the left, and the four differences give us an example of an explicit method. We can compute the next value of the approximation by evaluating the right-hand side. The modified Euler method is obtained by applying the trapezoidal rule to the right-hand side, and that is our first example of an implicit method, because the problem with Euler's method is that the next value that we want to approximate appears both at the left and the right-hand side. So this is another characterization of the methods we started with. In general, we talk about predictor and corrector methods. So Euler's method of Euler is an explicit method that can be used to predict the value that we need to run a corrector method. In general, the predictor method will always be explicit, whereas the corrector will be implicit. So let us generalize this. So Euler and the modified Euler are very simple methods, often too simple to be of use in practical applications. So we consider the family of Adams-Bashforth and Adams-Moulton methods. Here it is. So we are constructing formulas based on numerical integration. But rather than integrating over an entire interval, so going from 0 to x, where x is our last point, we actually integrate over the next interval. So we have a discretization. So we have a discretization where, so perhaps I should have pointed this out earlier. So we are discretizing here our interval. So we are considering not going the entire interval from x0 to xn plus 1, but we are considering from xn to xn plus 1. So we apply the integral operator to our differential equation. We compute the next point, the next approximation, as the previous point plus a correction term. And that correction term is the integral, the definite integral of an interpolating polynomial. So interpolation comes again. And here you see that both formulas use exactly the same conditions, but Adams-Moulton goes a little bit farther than Adams-Bashforth. They both use the same number of points. So the parameter is often also called the order of the method. So when used to, so the last sentence here is that what is the difference between the two? Well, the difference in the two, if you just eyeball it and do some pattern matching, we see the n plus 1. So this is where we have the one extra function evaluation. And that extra function evaluation occurs at the point where you cannot evaluate the polynomial, essentially. So the fn plus 1, so the fn plus 1 is actually at xn plus 1. So xn plus 1 here, and yn plus 1. So that is what makes the method implicit. So you want to construct an interpolating polynomial, but you actually don't know where to construct that interpolating polynomial at the very end. So that's why they are used in a predictor-corrector method. So the Adams-Moulton's method uses one extra point when it corrects. Here is a picture that probably is much more illuminating than the formulas on the previous slide. And we will rediscover or rederive Euler's method, which is now called the forward method. So the forward Euler method corresponds to using forward method to integrate. So we have seen the midpoint rule, and one approximates, so we must have seen this in calculus with the Riemann sums. So the forward and the backward Riemann sums correspond respectively to the forward Euler and the backward Euler. So the forward Euler method is derived by using here a very simple approximation for this integral. So the area of the green rectangle is what I just underlined. It's the approximation for the definite integral. One can be a little bit better by using also the previous function value, not only the current value at the current point, but you evaluate the right-hand side at the previous value at xn minus 1, yn minus 1, and you construct the line through those 2 points, and then we have a green trapezoid. So the highest, here the highest, so the second function value is obtained by evaluating the interpolating polynomial, which is now the blue line. We evaluate the blue line at xn plus 1. So in a way, it's also an extrapolation. So we use interpolation to extrapolate. Often this doesn't work that well, but for areas, it's actually okay. So here then we arrive at the Adams-Bashforth formula of order 2. And going from the interpolating polynomial to the formula at the bottom right here, what you do is you plug in, you replace the x by the xn plus 1. And you can see that the factor 3 comes from, so we have the minus fn plus 1. So the step size is fixed. So the xn minus 1 is h. And the xn plus 1 minus xn is also h. So it's a simple exercise to see that the formula at the bottom right is indeed obtained by the construction that is shown here. So you apply the trapezoidal rule to interval xn plus 1. So these are two Adams-Bashforth rules. How do we now construct more accurate Adams-Bashforth rules that use more function evaluations? So with 3 function evaluations, we are using not only the current function evaluation, but also the 2 previous ones. So how do we obtain the coefficients then? Well, we already know how to do this. We can apply the method of undetermined coefficients by requiring that if we do this, if we apply this integration rule, that all the basis functions are integrated correctly. So this is what we called the method of undetermined coefficients. So our Adams-Bashforth rules can be constructed by running a simple script that uses SymPy. So we used SymPy in the method of undetermined coefficients. So now we use it in a different setting. So we have our points, and we integrate from n plus 1. So we actually require that if our function would be a polynomial, which is a linear combination of the basis functions, that it will be integrated correctly. So we set up the integration rules. So we integrate now from xn to xn plus h. So our integral is different. So let me emphasize this. So this is where the application differs. So we have our 3 basis functions, and the right-hand sides will be the right-hand sides in the equation. So requiring, we have 3 equations, and the rule is defined here symbolically. So we have a function that will evaluate, apply the rule at those 3 points. The 3 points, 0, minus h, minus 2h. So the also important here, why do we change? Well, I should have pointed this out at one of the previous slides. So what we call xn plus 1, xn plus 2, or xn minus 2, what matters most is that we want everything in the parameter h. So that's why we relabel xn is where we are currently. So that's where we currently start. And then we look backwards. We look backwards minus h to minus 2h. So that is the relabeling. So we will obtain a system of 3 equations with a parameter h. And SymPy can solve this symbolically. So we arrive at then a 3 points Adams-Bashforth rule. having SymPy solve the equations and then copying the values for the three coefficients in this rule. All right, exercise 1, do this one step further. So the rules, now I can explain it a little bit better now. What I forgot to point out in my previous explanation is that we relabel the points. So the current point xn is labeled 0, and then we integrate from 0 to h. So in the construction here, this will be 0, and that is h. So in the SymPy script, we did this relabeling. So we have now 4 weights to determine in our method of undetermined coefficients. So you will add one extra line using one extra variable in the SymPy script and then run the script. And what SymPy then returns to you, you copy as the values for the 4 weights. Numerical integration again. So these are the explicit Adams-Bashforth rules. Then there are the implicit methods. So when we defined the Adams-Moulton rules, we said that then we actually also used the last point. So the point actually where yn plus 1 is needed. So that gives an implicit method. So we derived the backward Euler method last time because one needs implicit methods for stiff equations. So the backward Euler method does extremely well on that equation that we had last time, a rapidly converging function to 1. Here the backward Euler method is derived by the backward integration rule. So if we have the forward rule to approximate integrals, and we have the backward one-point methods to approximate definite integrals. So that gives rise to the backward Euler method, which is the simplest example of an Adams-Moulton rule. Now, doing this a little bit more sophisticated, we consider two function evaluations and consider the line. So the blue line here is the interpolating polynomial p. I didn't draw it all the way through. Perhaps I can do this as an exercise. So let's draw it. So we have the blue, so the p here extends. So this is the line, the interpolating line. We are interpolating and compute the area of the green trapezoid. So you see we apply the trapezoidal rule, and the rule is very familiar. This is the modified Euler method. So the Adams-Moulton method gives us here the modified Euler method. So we have derived now our forward Euler method, the backward Euler method, and the modified Euler method. So there are all 3 examples of Adams-Bashforth and Adams-Moulton's method. All right, so this is the modified Euler method. Let's generalize this again with the method of undetermined coefficients. So we want to use 3 function evaluations. We are going to define now again xn is relabeled to 0 when we apply our method of undetermined coefficients. And again, why is that? We want to find expressions for the 3 unknown coefficients in terms of the step size. So we use SymPy again to formulate the conditions on the rule. In particular, the basis functions are integrated correctly. That will lead to a linear system with a parameter h that SymPy can solve very easily, and that will give us the explicit values for the three coefficients in this rule. Here it goes again. The main difference, which I will point out now, so it all looks the same. The more we do different things, the more they are the same. But here, the main difference is now that we look not only back, but we also look forwards. So we have h0 and minus h. But we still integrate from xn to xn plus h. So this is where our method of undetermined coefficients differed from what we did in the chapter on numerical integration. All right, so let's look at the solutions. So here we run the simple Julia program, and that gives us the explicit values for the three coefficients. So we have a 3-point Adams-Moulton rule where we do the weighted combinations of the function values, knowing that this is implicit. What is so implicit about this? We here have the yn plus 1 that is sitting in there. When we want to evaluate this function at the right-hand side, we will need yn plus 1 sitting there. So knowing that the fn plus 1 is depending on the value at the right. So this is an implicit rule. All right, next exercise again, similar pattern. Now we use 4 function evaluations. So the function evaluation for the next step, the current step, and the 2 previous steps. So we have then 4 points and 4 unknown coefficients to determine. So in the exercise here, you will extend the SymPy script with 1 extra symbol, and we will have 1 extra equation for 1 extra basis function x to the power 3. So if the function is actually a cubic, it will be integrated correctly. So the order is 4. All right, so what have we done? So we have derived a predictor-corrector method that uses the previous function values. So we use a 3-point Adams-Bashforth rule to predict the value to use in the corrector. So here it is explicitly used. So the link between the two is the overlined value. So that is used, that is computed first in the predictor and then applied in the corrector. So only 1 new function evaluation is done. So we will see the relationship with the Runge-Kutta methods. So what is actually the point of all this? Well, the Runge-Kutta methods were of the same order, but they required many more function evaluations. So a Runge-Kutta method of order 3, which had a global error also of order of h to the power 3, required 3 function evaluations. So the local error of a 3-point Runge-Kutta method is h to the power 4. And and that's also the same error of the same local error of the Adams-Bashforth Adams-Moulton. So how do we see this? Well, we integrate the interpolating polynomial. So we integrate the error term. So remember, the error term was x minus x naught, x minus x1, minus x2. So here, this local error here is actually the error of the, we have the interpolation points 0, minus h, minus 2h. So that is the same error that we had as with the interpolation. So that is the term in h. The global error is always n times, or 1 over h times the local error. So the 3-point Adams-Bashforth Adams-Moulton pair uses one new function evaluation and gets the same accuracy at Runge-Kutta methods. So why bother then to use Runge-Kutta methods? Well, at the start, you don't really have anything. You don't have any previous function evaluations. So about Runge-Kutta methods, if you have a 3-stage Runge-Kutta method, you use 3 function evaluations and you have a global error of h to the power 3. So that's the most important thing that we know from Runge-Kutta methods. The Runge-Kutta method of 3 stages is used to start up the Adams-Bashforth Adams-Moulton. So here this is explained schematically. So we start at x0 and we want to compute y1. Y1 is computed with 3 function evaluations. So here is where what we write, and this is very summary. So this is the cost that we do at our first step. We get y1 here. That's our first approximation. We then compute y2 with another 3 function evaluations. So when we are at x3, so this is where we have y0. So that's our initial condition. And at this stage here, we can, at x3, we can use an Adams-Bashforth Adams-Moulton pair. So the Adams-Bashforth rule on the previous slide with the 3 function evaluations, it uses y0, y1, y2. So no new function evaluations are necessary to obtain the predictor, so the overlined value for y4. And then we apply the 3 function evaluations plus 1 extra function evaluation to obtain y4. So going to the next step, the amount of work that we do, again, evaluating the right-hand side could be a very complicated program, and that determines the cost. The cost actually drops a factor of 3. So that's important, why these are so important. Okay, so this is important here. So this motivates the use of predictor-corrector method in conjunction with the Runge-Kutta methods. So what's the point of using predictor-corrector method? So we have arrived the 4-point method. So this could be another exercise, but here work this out now specifically. If you want to go to the value 0.8 using a fixed step size. So how do you solve this exercise? Oops, think about, this is kind of wobbly, but think about a discretization. So here I have 1, so this is 0.1, 1, 0.2, 0.3, 4, 5, 6, 7, 8. And I'm actually doing this exercise now. So to compute the value here, you are using 3 function evaluations, 3 function evaluations also here. So let's start like this. You did 3, and then we do 1, 1, 1, 1, 1. And here we then get to the 0.8 value. So the total number of function evaluations is indicated on top of this line here. And that determines the cost. So compared with the Runge-Kutta method, you have to multiply 8 times 3. So you do 24 function evaluations in total. All right. This was the class of predictor-corrector methods. That is used in conjunction with the Runge-Kutta methods. Runge-Kutta methods of the same order as the predictor-corrector methods. All right, then another class of methods. So we obtain a value for the next step by adding something to the value of the previous step. One can generalize this and make a weighted combination of the previous 2 approximations for the function. So the y's are the approximations for the solution of the initial value problem. So we have a weighting, so A1, A2, and then we add to that a correction term. And again, we will apply we can apply the method of undetermined coefficients, but here we apply Taylor expansions to set the coefficients. So the 2 coefficients that we use in the combination of the current and the previous value, and then also the step for the value for the multiplier for the function value for the right hand side. So how do we do this? Well, we look at the method here. So here is a method which is a 2-step method which uses 3 function evaluations. So the previous example was a 2-step method with 1 function evaluations. And here we having implicit methods. We can turn this method in an explicit one by setting the B naught to 0. So we have now 2-step methods that use multiple function evaluations. So this is now a combination of implicit and explicit methods, but in a multi-step way. All right, how do we derive these methods? So we can develop the Taylor series expansion. So here we have the Taylor series that is truncated after the first 5 terms by 5 unknown coefficients. And by applying then the Taylor expansions further to the Fn plus 1, the Fn and the Fn minus 1, one can derive conditions on the unknown coefficients. So let us not explore this Taylor series expansion, but let's now try to judge which methods are better. So here we have 2 explicit 2-steps methods. And again, it's similar to the methodology that we used for the Runge-Kutta methods with the Taylor series. So these methods occur in family. So here we have 2 explicit methods, and they are of the same order. So obtained after truncating the Taylor series after the fourth term. Now, which method is better? So the first two-step method averages. The second method, which is just from the Taylor's perspective, from the local order perspective, just a good enough method, will subtract from the previous values, will subtract the current value in the two-step. And then one has other combinations in the right-hand side. Which one is better? How can we answer this? Well, we can look at the stability. Here is what the second method does to a very simple initial value problem. So it's no longer exponentially decaying. We have a solution that is actually flat. So it's a very trivial test problem, but let's see what we apply to this. So if we apply the method with the exact zero condition, then we will indeed always add 0 to it. So no problem there. So starting at 0 will produce 0. But suppose that we don't start 0. Suppose that we would start something different from 0. Can always happen with a round off. How can we see that, and how can we then obtain other solutions? Well, we can obtain solutions that are growing in size. And how is that possible? Well, if we are substituting the solution that we expect. So we have a solution that depends on parameter lambda and power n, so a constant c in front of it. If we solve this in the equation, this is a fixed point, we solve it, then we see that there are two values for the constant. So we have the constant where is 1, then actually we have a constant solution, and that constant needs to be 0, fine. But we also have another solution. So lambda is -2, then we do have, it's still an exponentially decaying solution, but still it is a non-zero solution. So let's try to do this also for, let's look at the other method. So we will do the other method in the same fashion. We will have a general criterion to decide whether a method is good or not, a multi-step method is good or not, which essentially ignores the H part, which ignores what comes here. So we look at the coefficients, and we use the coefficients to define a polynomial. So how that polynomial came to be was hopefully illustrated by the previous example. So the roots of the polynomial were actually critical at finding other solutions that the method might produce. So the other method, the other solutions that the method could produce are determined by the roots of the equation that have the coefficients of the multi-step method in it. So if all the roots, if some of the roots are an absolute value larger than 1, and that was the case with this -1. I misspoke and I said that the solution is exponentially decaying, but if you have even powers, then you take even exponents. If you have the method, if you look at the previous method, 2 to the power h for odd powers, you have indeed small values because you have the negative sitting in. No, you still have large values, but they are very, very negative. The method is indeed diverging. So if you have roots that are larger than 1 in absolute value, you do not have stability. Formulated more positively, if all roots of this polynomial are less than 1 or at most 1, then your method is stable. If there is only one root and that root is 1, then you can have only one solution, and the method will then be strongly stable. So going back to the previous example was not stable, was not a stable method. Same order, but not stable. What you will do as an exercise, you will determine the roots of the polynomial, a second degree polynomial, where the coefficients are 1/2 and 1/2. Is this stable, and justify why that is. Is it strongly stable? So if one is the only root. So this is an explicit two-step method which will be stable. All right, multi-step methods. So we've seen predictor-corrector method, multi-steps. We can also have variable step methods. And I will conclude this lecture with simple examples of methods where we use different step sizes. Here is an example of a variable step size of order 2, where we use the Adams-Bashforth method. So here is a picture again of the Adams-Bashforth method. So the picture is the same. Basically imagine the differences between the points between xn and xn minus 1, and xn with xn plus 1. They can step size. We are using different values, different step sizes. So can we then derive also a formula? Well, yes, we can. So here you see the generalization of an Adams-Bashforth method with two function evaluations. So a 2-point Adams-Bashforth variable step size method. So we have the same interpolating polynomial, so that it is a line. And we evaluate it at xn plus 1, but now actually the h values no longer cancel each other out. We have an hn and an hn minus 1. And these two interval sizes, so these two step sizes, also appear in the formula. And you can see that if hn equals hn minus 1, like on the picture that I have recycled, then we have the coefficients 3 and -1 in the Adams-Bashforth method of order 2. All right, last exercise, find variable step Adams-Moulton method. So I was too quick when I copied this. So this would be Adams-Moulton method. So I will have to fix this. So this is an Adams-Moulton method. So we are, so the question here now is to derive the 2-point Adams-Moulton method, where you use the trapezoidal method. So instead of having h divided by 2, you will have hn divided by 2. So as a matter of fact, the hn-1 will not factor in. All right, not all exercises are as hard. Just knowing the concepts matter. Which brings me then to the last slide. So in this lecture, we close off our discussion on initial value problems, where we derived methods based on numerical differentiation and numerical integration. So that gives us Euler's method and the modified Euler method. There is the problem of conditioning, so the sensitivity on the initial value. Before that, we have to be aware that if we want uniqueness, we need Lipschitz continuity. Many interesting applications are modeled by higher order equations, and we can rewrite every higher order equation as a system of first order equations. If the system is linear, then actually the eigenvalues of the matrix of the linear systems characterize whether the solution is growing, so if we have exponential growth decay, or whether the solution is oscillating. Oscillating growth and oscillating decay. For Runge-Kutta methods, P stages, so a P-stage Runge-Kutta method uses P function evaluations, and the global error is also h to the power p. We encountered the need for implicit methods when we solved stiff equations, for which the explicit Runge-Kutta methods actually are not working quite well. We have ended this lecture with predictor-corrector methods, which can be explicit one-step or multi-step methods. We apply the predictors to get the correctors going, and correctors are implicit methods. So next time we continue with ordinary differential equations, but then we consider boundary value problems.